Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello, Senior 6 Chemistry students. Welcome back. I'm happy and excited to still be with you in the chemistry lessons. Alan is my name. So we are still on our topic, chemical kinetics, and unit 14, which is about rate laws and their measurements. Right now we are going in for lesson 2, rate law and the order of a reaction. Please join me. Okay, so before we actually look into today's content, let's take a quick review for some of the students who are possibly joining us and they weren't there in the previous lesson. So let's bring them to the speed of what we covered in the previous lesson. And of course, we covered about the speed or the rates of reaction. So in that lesson, we looked at the fact that you can determine the speed of a moving car looking at the distance it has traveled and in a specific time interval. So in that way, we use speed as distance over time. If you can use kilometer per hour or meter per second, depending on the units you opt to use. So in the same way, reactions, you can determine their speed, which we normally call rate, by looking at any detectable physical change with time. For instance, the change in mass as the reactants are producing products, their mass reduces. So you can follow the reduction as time passes, and you measure the rate of reaction. Or you can use the volume and a lot of other more physical quantities as you can see through, or as you can see them. So that gives us the aspect of measuring the rates of reaction. So if we look at, for instance, concentration as a sum up for all those physical quantities, you notice that for the products, the amount increases, and for the reactants, the amount reduces. So in that way, you can follow either the decrease in the amounts of reactants or increase in the amounts of products. As you follow them, then you can determine the average rate for that reaction or instantaneous rate. Instantaneous rate, that is the rate of a reaction at a given time. So looking at the average, we said you just look at the total changes in your reaction. For instance, this was for production of hydrogen. You see it increases as time passes, so up to a point whereby the reaction will cease to occur. So when you consider the total changes with the time taken, then that gives us the average rate. Also, through the experimentation, you can directly get rate at a certain time, and that is by calculating the slope or the tangent at that point, as you see in this illustration. So briefly, this is what we covered in the last lesson. As I told you, I'm just bringing you to speed if you happened not to be part of that lesson. So right now, let's look at today's lesson work. Lesson 2, rate law and order of a reaction. As usual, I have to bring you to the concepts that we shall go through and the key terms and the objectives. So today we shall look intensively on the exercise that I left you with. We do a few corrections. Then we introduce the rate laws and the order of reaction. So that is what will make up today's work. And from what we shall cover, you notice the key terms. the key terms. The first is rate law, or we normally call it rate equation. Second, order of a reaction, and the third, the overall order of a reaction. Those are the key terms we shall be describing and defining in our lesson. And the lesson objective, to formulate and explain the rate law, or to formulate the rate equation that describes the relationship between the concentration and the rate. Then we explain the characteristics of the order of a reaction. Those are the objectives as regards to the key lesson terms and the content to be covered. I hope we are at the same pace right now. Even when you weren't there last time, I think you can pick up. So this is the exercise I left you with. Remember, in one of the aspects that we are to look at, we are to go through it extensively, understand it, so as even when we don't do other more exercises, you are very comfortable with any question that would come on rates of reactions. So I told you, get the graph paper, plot, and go through those questions. So I want us to go through them together as you refer to your responses. Get your calculator, get your graph paper where this work was done, then we grade it. Question 1, use a graph paper, then show the valuation. So that is the answer. What is very crucial on this part? I want you to look at your graph paper and see if we have similar information. I'm not saying the same because this is graphing, indicating I expect almost each student to have different work from the other, since you're going to be using different scales. You're going to be using even some of the graph paper you're going to use will have different squares. The size of squares may be different, so we may not have exactly the same, but it should be similar. It should conform to same principles. What are they? You need to have the title of your graph. Always ensure to include the title on your graph. Include the y-axis. Label it. As you see, the volume of hydrogen gas in cubic centimeter. That is the label for the y-axis together with the units. Then we have the x-axis, as you see, time in seconds. So at least those are the three principal parts that you should never miss on a graph. Then you can put the scale of your choice, which conforms best, and the scale of your choice, depending on the data you're having. So from the data we're having on the table, this is the possible graph. To me, I use on the x-axis or the time axis, I use the 30 seconds, the interval 30 seconds, whereas on the volume, I use the interval 555. So you get such a kind of a curve. I guess you've corresponded with your graph. We are in the same way, right? Yeah, I will sometimes surprise you and come and check your work. You better have it corresponding to what we are going through. So that is question A. Question B, determine the average rate of the reaction between zinc and dilute hydrochloric acid. So this is the setup to get the values. This is what was used. You see the timer and the gas syringe, where the gas that is being produced was collected. So how do we get the average rate? Remember the calculation. Average rate, total changes over time taken. Now let's refer to our table. We are actually going to see two different approaches, but let's first go through the table and see. What do we see on the table? At the end of our experimentation, after 300 seconds, certain volume was corrected. So indicating this is the total volume in accordance to the time we had. Why do I call it total? Because as the gas is being produced, look at my highlighter. As the gas is being produced, it is collected in the syringe. So the more the gas, it pushes the syringe, so we have the whole container, 34 cubic centimeter in this syringe. So this is the total volume, this is the total time taken. And so we have our average rate for that reaction as 0.113 cubic centimeter per second. Units, look at the units. You don't need to miss those units because the rate, the units can actually tell us what was happening. Did you measure in terms of meters? Did you measure in terms of what? You need to include those units. So that is the first way. I believe some of you used the graphic method. You had plotted your graph, right? So to get the total changes, just look at the highest point on your table, which will give you 34. Then from the starting point, which is 0, if you use that scale. So it will be 34 minus 0, which directly gives you 34. Then the change will be the highest point of the experimentation, which is 300 minus 0, which again gives you 300. So either directly from the table or from the graph, it would give you the answer. That's why in this case it was saying determine. It wasn't specific on whether you have to use the graph. So I give you a minute to look through the different approaches and see the answer. Is it what you had gotten? Let me believe that is what you had obtained. Part C, the average rate in the first 90 seconds. What you may think these questions are the same. No, they are not the same. They are different. The aspect in here is for you to grasp the concept of the rate of a reaction. You can determine the rate of reaction at any moment within the reaction. And this is what we are looking through. Or you can determine the average rate of a reaction at any moment after the reaction had started occurring or has started occurring. So you can determine that. For that case, within the first 90 seconds, you notice the volume that has already been collected or accumulated is 20 cubic centimeters. So indicating we have the total time, which is 90 seconds, and the time and the volume accumulated. We just simply substitute in our formula and get that. That's the value. You can actually get it from using the graph in the same way. You would now consider, like the way we did in the first, you would consider all the changes within the 90 minutes, which would directly give you that. Get 20 minus 0. 90 minus 0, which would yield to this again. That's C. Let's go to D. D is about instantaneous rate, the speed of a reaction at that given time. So we have for both 60 and for 210 seconds. This is slightly different compared to the average rate. So how different is it? Let's consider all the two cases at a go. Take a close look at my calculation relative to yours. I'm giving you a minute. Take a close look at these graphs. The one of at 60, you see, you draw a line up to when it meets the curve, then you find the tangent at that point, or you find the slope at that point, which would be the y side and the x side, which directly gives you the value. So it is 0.192, and at 210, the same calculation, it gives us 0.58. This is the value. You see the working. The working is highlighted. Let me not take much more time in there. So that is how you quickly look at the instantaneous rate of a reaction. Lastly, compare the rates of a reaction at 60 and at 210 seconds, respectively. How are they comparing with each other? And explain the answer. So what did you find? Tell me your comparison. What do you see? Or what did you come up with? Someone sharing? Yeah, if you have a friend, share with that friend or discuss with a friend. But let's now converge and see. As you see, at 60, the rate is 0.192. At 210 seconds, the rate is 0.058. It is decreasing. That is what we all can see. So that means at 60, the rate is higher than at 210 seconds. Or you can say the rate at 210 is lower than the rate at 60. Either way, the way you state it, do not have a closed mind. Think outside the box. So in that way, you can give the explanation. What makes the rates to be higher at 60 second point than at 210 second point? It's all about the concentration of reacting species. As you know, when the reaction starts and it progresses, the concentration of reactants decrease. So we expect closer to the start of the reaction, the concentration to be higher than after some time when the reaction has started. And that is what exactly happens. The values speak louder than words. Looking at those values, you can directly tell which stage of the reaction the reaction has gone up to. So that is what we can quickly look at in terms of measuring the rates of reaction. And of course, I can't miss telling you the day-to-day applications of rates of reaction. Day-to-day applications of rates of reaction. Of course, some of you, let me actually bring this onto you. Have you ever asked yourself why they give you 2 tablets to take at a go, or sometimes they give you 1 tablet to take, or 1 capsule, and then they tell you, you take another dose, maybe after 4 hours, maybe after 8 hours, maybe after a whole day. Have you ever asked yourself why? Or have you ever bothered asking the doctor why? That is for you to think about. So it's just about the rates of the reaction of that drug in our body or in your body. So this takes us today to the everyday life applications of the measurements of rates of reaction. They are for diagnostic reasons, or this is a diagnostic tool in a sense that it gives idea to the chemists on how the drugs they are making, the fertilizers, all these items that are manufactured will interact with our bodies, within the environment, and so on. Going back to the drug, normally when a drug is made, they have to ensure that they know how long it will take for it to react within the body and how long it will last in the body. So as they can know when you're to add another amount of the drug or when you're to take another dose, if I can use layman's understanding. So without the knowledge of the rates of reaction, there is no way scientists or pharmacists or doctors would directly know that the drug will last in the body about 4 hours or it will last in the body about 8 hours. So as you add in another dose. So that is made possible due to the measurements of rates of reaction. Since those drugs and chemicals, they are actually made up of molecules, and so they react whenever they interact with something. And that is the application of rates of reaction in our day-to-day life. Words are just there. I was explaining what happens. So now we can now move to the second objective, which is about the rate equation and the order of a reaction. Rate equation and the order of a reaction. So, rate law. Basically, when we take of rate equation, we are looking at that mathematical equation that describes the progress of a reaction. Mathematical equation. So we are now relating the rate and the concentration. How are the two related? Suppose I have, in a reaction, I reduce the concentration. How will that affect the rate? Suppose I increase the concentration. How will that affect the rate? And so can we bring those words and the real molecules reacting to a uniform way of understanding? So as if any person comes and looks at that word or looks at that formula or that expression, understands exactly what is happening. So that is basically the rate law, rate equation. So chemically, if you have two reactants, let's take A and B reacting to form products, the rate law or the rate equation is rate, the rate coefficient or specific rate constant, concentration of that reactant raised to a power, and concentration of that reactant raised to a power. This is basically the rate law. One will ask, what is A, small a, what is small b, what is all that? What does it mean? What is this basically? Where does it come from? I think that is rotating in your mind. Let's now go through and see where it comes from. We looked at collision theory, didn't we? Yes, we did at the start. So for products to be formed, reactants must collide. And if you have more reactants, then high chances of collision. When I talk of more reactants, I mean in terms of concentration. So the rate is directly proportional to the concentration of the reactant. At least one should have the concentration which is appreciable to allow those collisions. So this gives us a mathematical expression, rate directly proportional to the concentration of reactants. Still on our general equation. So suppose we keep concentration of B constant. Suppose we don't have B, we assume it is not actually there. What will happen? That means the rate will only be depending on the reactant A. So that gives us rate directly proportional to the concentration of reactant A. Let's remove the proportionality sign. We bring in a coefficient which is K. This A is the power, which is the power raised to the concentration of those reactants. So suppose we also make A constant and consider B, the same thing. So when you combine those two equations or those two conditions, it gives us the rate expression, or it gives us the rate equation which we have here. So let's understand what is A, what is B, and what do they imply. I've already mentioned the K as the rate constant. So A is the order of the reaction in regard to A, then B is the order of reaction with respect to B. Overall order, it is when you add those orders per reaction or per reactant. Let's understand those two terms as we come close to the end. Order of a reaction. Just the power to which concentration of the reactant is raised to. Overall, just sum them. So you may wonder, what exactly is the order of a reaction? What does it imply? What is it exactly? Characteristics of the order of a reaction. Basically, that order of a reaction, it can be a whole number or it can be a fraction like here. You can have a 0, you can have 1 or whichever value there. So the order of a reaction, if I can bring it to layman's understanding, is basically how does the change in concentration affect the rate. Instead of using it in words, we want to bring it to a mathematical expression. We want to bring it in numbers. We want to make it quantifiable. That is what is happening. So if you have a 1 here, what does it mean? If you have a 2, what does it mean? If you have a 3, what does it mean? So we are bringing those words to numbers. That is basically the order of a reaction. So that is it for today. Thanks for being part of the lesson. And we're going to start directly from there. Thank you. Stay safe. Bye.